Going? Good? Bad? The RL project? What's that? Not? What? Not quite yet? Yeah. Start early. We think it's not as bad as the other ones, but we don't know. So definitely start early. This is the last lecture on RL. Yeah, Lee? Oh, just saying hi. Okay. This is the last lecture on RL. We're going to cover Rmax today. That's the last algorithm that you need to do for your project. And then this coming Thursday's lecture is going to be a guest lecture by James McGlashan. He's Michael Lippman's postdoc. It's going to be really good. He's going to talk about his reinforcement learning framework called Burlap and some of the stuff he's doing with like ethics and moral reasoning and stuff for RL. I think you'll really enjoy it. And then after that, we're going to switch gears and talk a little bit about robots. It's kind of putting a whole picture together. And then the final. And there's Thanksgiving in there too, so like that's. But it's sort of all coming up. So any questions or anything before we get into today's lecture? Yeah.
We have two finals, right?
You have finals in 2 different classes. Yeah, 2 different class sessions. And we're going to do a paper final this time. We decided to try that way instead of edX. And we're going to make it shorter. Each one will be cumulative. So it's not like you're going to study some subset on one day and another subset on the other day. The reason for that is that part of the point of these tests is to make you study. And that helps you learn the material. It helps you get into this, like I said this before, like this kind of feedback loop where you're trying to figure out what you don't know and learn it. And so I think making them not cumulative doesn't really serve that larger goal. And it lets us ask questions that kind of integrate things together across different parts of the course to try to see how well you can put the pieces together.
So final work, how all this math?
What's that? Yeah, it's going to be cumulative over the entire course. We're still working on that. We were talking. I think this room is going to be too small if everybody shows up, and the desks are kind of crappy. So we were talking about having this room and a room in the CIT, but as I was walking over here, I was thinking that's going to be hard because I'm going to have to run back and forth or not see people who are over here. So I was actually thinking we should try to get a CIT room. So stay tuned for more information about how we'll solve that problem. Probably depends on what rooms are available. More questions? All right. So today we're going to kind of finish we're doing this journey through RL, right? So we started out with value function-based methods where we're doing Q-learning. And then last class we talked about bandit problems, and then we talked about Thompson sampling, which is an example of a model-based method, right? We knew over these bandit problems were pulling the slot machine, the one-armed bandit. We knew the model. We actually knew because we programmed up our own little AI Vegas slot machine. And we knew what the model was like, and then we were able to define, with Thompson sampling, this really nice way, okay, there's a prior on the distribution, it's actually uniform, so that translated as this Dirichlet, the beta distribution, that was really flat, remember that? It was really flat, and then we did an update, and that was the one that performed the best. That's an example of model-based. But the problem with doing that, is it's pretty hard, and people do it, it's pretty hard when you get to more complicated problems from these bandit problems to come up with a well-parameterized model. So people do there's other variants of model-based methods. They still try to learn a model, but they don't do it in the same. They don't try to model every single thing about the domain. Or they're more coarse-grained. They're sort of more at the MDP level, and that will give you less than Thompson sampling. Well, for example, on these bandit problems, because when you're doing Thompson sampling, you're putting a lot of your knowledge into the RL algorithm. That's the way to think about it. And when you do that, you give the algorithm a chance, by telling it how you think these numbers are coming from and how do you think the model works and doing the updates in this way, you're giving the algorithm a major advantage by putting that knowledge in. And that's often a way to make these systems work a lot better, by putting your own knowledge into it. But you don't have to, and there's other algorithms you can run, so Q-learning is an example, and there's policy-based methods. Where you can try without putting as much knowledge in, and sometimes it works anyway. Sometimes things don't work, and you always have to think pretty hard to make this stuff work. But you have to sort of figure out different ways to putting your knowledge in to make things happen. Okay? Any questions? So this is a Q learning from before, from 2 classes ago now. But we did it briefly in the last class too, right? So like, this was this idea that we're going to update the value function, right? So we're going to do this TD error kind of deal here. The difference between our expected Q value and our observed reward at 2 states up there. And then we're going to send our estimate of the value function in the direction of the TD error. And that alpha was how big of an update we were going to do. Does anyone remember how we actually, like when we were doing Q learning in kind of online mode, how do you actually get a policy from this? What do we have to do? Yeah.
So we have the state and we get the action which gives the max Q assay.
Right. So we're learning our value functions. When we get to we want to get to a policy, we take the state, and this is kind of buried in this thing here, but like we take the state that maximizes our Q function, right? So we just argmax, look up our current state, we find all the actions, and we pick the one that maximizes the value. So if you remember the Python code, it was just this max of this big matrix with the colon, right, to say, give me the best one of all the actions, and then go off and do that action. And how do we handle exploration versus exploitation in the Q learning? What do we do? What happens with Q learning if you always exploit, you never explore? Yeah. Yeah, you get stuck in local minima. So what do we do to avoid that problem? Yeah, so you could do random for a certain amount of times. That's called to do off policy for a while, just kind of randomly explore. What was the other thing we did? Like my favorite thing, everybody's favorite thing in the literature. We did do off policy yesterday in last class too in Thompson sampling. That's not what they're doing here, I don't think. But yeah, epsilon greedy. So that's the one. That's your go-to one. Like that's the one I want you to try first when you're implementing stuff. Epsilon greedy. So what was epsilon greedy? What did we do? Yeah, so most of the time we act according to our learned policy. We try to exploit, but some amount of the time we explore. We go randomly. So that's kind of, I kind of wanted to like review where we were with Q learning before we sort of switched gears and talked a little bit about model-based RL. And that's the Rmax section. We'll get to Rmax. That's the Rmax section on your project. So model-based RL, this is like a picture from the paper that we linked to on the website that kind of gives a survey of the whole thing, and it also describes the Rmax algorithm. It's not in the book, so that paper is our recommended resource for reading if you want to read to understand how this algorithm works. And basically what happens is like you do stuff in the environment, you get a state and a reward, then you update your model. Then you use that model to get a value function. And then the value function gives you an action. So first of all, what's the difference? If we wanted to make this figure for Q learning, what would it look like instead? How would we change this figure to make it be Q learning? Which block do you think you'd have to change? The blue one or the green one? Yeah. The green one, yeah, that's a good clue because it's inside the agent, right? So it's the thing inside the agent. So what about that block do you think we need to change? Yeah, so the Q function is basically the value function, right? You can kind of convert from one to the other, and if you just do the Q function, you don't need to do that transition dynamic stuff. So you just wouldn't even need the model. You just exit out. The state action stuff comes, it updates your value function presentation, and then that gives you a policy. So model-based sticks this model stuff in here. So let's think back to like what's an MDP. So what is an MDP? Let's write that down first. And then we'll say which parts of the MDP are the model, or do you think are the model? What's an MDP? What are the parts of an MDP? States, yeah, good. What else? Reward function, yes. What else? Actions. Good. Put R down here. One more thing. What's that? Yeah, what probabilities? Say it again. Yeah. So we want some probability distribution, and it's going to tell us something about the next state. It's going to be given an action. It's going to be given one more thing. What's the other thing you're given? Your current state, yeah. So I'll put an S prime and S. Yes. So this is the probability of S prime given A and S. Sorry if you guys can't see it over there. And what do we call this? Transition function, yeah. States, actions, traditions, and rewards. So that's my MDP. And then remember, the first lecture, this whole thing was about like MDPs and solving MDPs. We want to get a policy, right, that told us for every state what's the action that we should be taking in that state. And to do that, we did like VI. Then we switched gears. We said we're not going to know the transition function for RL. We're not going to know the transition function. We're not going to know the reward function. We're going to try to learn them. So Q learning was trying to learn the value function and go from that to get a policy. What do you think model-based is trying to do? Yeah, it's trying to explicitly learn the transition functions and the reward functions. Okay, so you took them away. Rmax is going to give it back to you. And then once you have the transition functions and the reward functions, then what do you do to get a policy? Kind of up there already. So now Rmax, your algorithm, somehow it learned the transition functions and the reward functions. Now what do I do? What can I do? What's that? Yeah, value iteration. Or pick your favorite planning algorithm. There's more planning algorithms besides value iteration. Value iteration is one that is known to converge to the optimal policy, but it doesn't. It has to enumerate all the states in the state action space. So there's sampling-based ones, and there's ones that. So the sort of intuition behind a lot of the faster ones is they don't run through the entire state space in order to get a policy. You basically pick your favorite one. That take your favorite MDP solving algorithm once you've got that model and solve it, and that gives you a policy. So I want you guys to take a couple of minutes talking to each other, and I want you to think about two things. So first of all, I want you to think about how you would learn the model. So how would you learn the transition function, and how would you learn the reward function? And the second thing I want you to think about is explore versus exploit, and how that would play out in these model-based methods. Go. Yeah? What's that?
Is this like a really tractable state space, or is this like a very explosive state space where it can't be infinite?
We're going to start out thinking about tractable state spaces, but I think it's interesting to go towards explosive ones, and we'll do that later in this lecture, actually.
I feel like it'd be easy to find the transition function where you can just enumerate over all the states.
Absolutely, yeah. And that's what your project is going to do. Yeah. 10 more seconds. All right, finish up. All right, so how would you learn the transition function? Let's start with the transition function, T. How would you learn it? What would you do? Yeah. So you can just have your guy wander around the world, wander around, and then every time you are in an S and do an A, remember S prime, right? And maybe like count stuff up. Okay, so you could imagine something like we were doing for your machine learning stuff, where you're counting out how many times these words co-occurred. How many times was I in this state, and it took this action, and it took me to S prime, right? And then how could I convert that to probability? What's that? Yeah, maximum likelihood estimate, right? So I could say, well, the number of times that I took S, and I was in A, and I ended up in S prime, those three, divided by what? Yeah, the number of times I was in the state, and I took the action. Right, so then, and I ended up anywhere else, or actually, it's everywhere. To make it normalized, it has to be everything. But like, it's summing out over all the other places I could have been to. Okay, and that'll give me a maximum likelihood estimate of my transition function. What if I wanted to be Bayesian? What would I do? What would I do? Yeah, I'd have a prior on my transition function. So it would look like that beta distribution, right? Like I might think that, and you might actually do this. Like you might decide, well, I think that most of my transition dynamics are local, and I maybe know something about what that means. Like if I'm here and I take any action, I don't think I'm going to suddenly end up in the CIT. You know, some kind of local constraint. So you can imagine putting that into your prior, saying like, well, if I know something about how far my states are from each other, I'm going to say that like it's pretty unlikely that I'll transition from here to I'll teleport myself from here to the CIT, right? There's quantum tunneling, but you know, unlikely, right? And then you get some kind of more complicated mathematical update, but it might smooth out, it might generalize better. And there's a whole field of Bayesian RL. They're kind of known for making algorithms that are really beautiful and that are like provably optimal, but you're not actually able to run them on large problems because the math gets too complicated. You can't take those integrals when it gets too big, even though it's like what Jane says we should all be doing. All right, what else do we have to learn for model-based RL? Reward function, yeah, so let's write that down. How would you learn the reward function? Yeah, so you could again do like a maximum likelihood estimate. So like you just count up, you're in state S, you took action A, and you got reward. And you can compute the average of that, right? The mean reward you got for that state, and that gives you knowledge about the reward function. All right, so then the last thing I asked you to think about was exploration versus exploitation. So when you said for the transition function, you just wander around randomly for a while and then sort of switch back and start doing exploitation. Was that the only thing you could do, or are there other policies you could imagine for deciding when to explore versus when to exploit? What's another thing you could try? What's my favorite thing? Yeah, epsilon greedy. So you could decide to do it just like you did with Q-learning with epsilon greedy, and sometimes act optimally with respect to your model, and other times not. And people do that. People do epsilon greedy. If you have a model, though, do you think you could do? You can kind of do better than that. So what's dissatisfying about epsilon greedy? Like we like it because it's really simple and it's guaranteed to cover the whole space, right? But it's not. There's something a little fishy about it. I don't know if you guys feel that, but I think that, yeah.
Even much later, once you've built up a really good model,
yeah.
You're still not acting up.
Yeah. So first of all, you're always going to be doing that greedy stuff. Remember our epsilon greedy algorithms for Thompson sampling? Like they were at the end when they'd converge, they were facing this permanent penalty for that exploration, because they might not have been finished with their exploration. They never knew when they were done. That's good. So what else might be bad about that, about epsilon greedy, besides not knowing when you're done? You're just going to randomly wander around and flip coins sometimes. So what kind of happened? Like, imagine you've wandered around for a while and you know some parts of the space and you don't know other parts of the space. What's epsilon greedy going to do? What would you want to do? Like, let's say you've explored some parts and you haven't explored other parts. You kind of want to go to the unexplored parts. Yeah, you kind of want to go and look where you haven't looked before. And why do you want to do that?
Because there might be something better.
Yeah, there might be awesome cookies over there. You don't know. You've never been there. So you want to go over and check that out. Will epsilon greedy do that? No, epsilon greedy will not do that. It will just kind of wait in the limit at the end. Eventually, it'll get there because it's going to get everywhere. But it's not going to bias your exploration towards those parts of the state space that you haven't seen yet. So using these model-based methods, you can actually kind of get towards some of that behavior. So how might you do that? What's that? Yeah, right. So what you can do is basically hack your value function, hack your reward function. So like when I've observed the reward, I know something about it, but so maybe I should have the problem first, right? So if I'm using Rmax and I've got some data and I run my value function solver, or I run VI or something, is that ever going to decide to explore what's it going to do if I don't have reward function values? What's going to happen when I run VI? I mean, it kind of depends on what I do about not having reward function values, but yeah. What's that? Yeah, so it kind of depends on how I treat not having a reward function, right? So if I set those unknown rewards, I could pick the number for those unknown rewards. I could set it to be really low, and then it would avoid those states. Or I could do what you said, and I could set the rewards for those unknown states to be really high, and then it'll be like, oh, dude, I got to go check out this place where there's awesome cookies, and then find out when it actually gets there that really the world was not as good as it thought it was, and then get kind of disappointed. And update to do its little update, and then next time go to another different state that it hasn't visited before, and come back. So that optimistic reward function initialization. If our agent is doing this in a kind of model-based way, what's the agent going to do when it explores, when it's learning? If we set the reward to a large value when we haven't been there before, what's VI going to do? What's VI going to do if the reward's high in a state, regardless of why it's high? What's the policy going to tell the agent to do? Go towards that state. Yeah, that's right. So if I artificially set the reward to be high, and I run in my learning algorithm at the beginning, if I set the reward to be high for these unvisited states, what's VI going to do? It's going to go towards those states. Then what's going to happen? Once it visits, let's say it goes to one of those states and visits it, and it observes a really small reward. It does a maximum likelihood update of that. What's it going to do the next time? Yeah, it'll avoid that state in favor of another unvisited state. Okay? So by doing this exploration bias, it'll think the world is really exciting, and it'll systematically go through and explore all those states and find out that actually most of them aren't so exciting. It'll do its update. And then eventually, when it's finished doing all the exploration, it's visited every state, it's going to decide, of all the places I've been, this was the best place to be, and sort of converge to a policy. Okay? So this is the intuition behind Rmax. It's called Rmax because we're going to do this. We're going to set the rewards to be some max value when we initialize our learning algorithm. And what that makes happen is it decides it's going to go out and look in these unexplored states. And it'll actually plan to go there. So when you start at the beginning, you're like, let's say you've explored over here and you've not explored over there, it'll kind of try to get itself over there based on what it's already learned about the state space to try to expand the rest of those unexplored space. It might actually make long-term plans to go and explore somewhere, because VI is going to do that, right? It's going to see, oh, there's some good cookies over here. I'm going to go over here and try and get them, and then they're going to disappear from. They're going to dematerialize when it actually gets there, because we did this optimistic bias. But when it gets there, it's going to collect the information about what it's like to be in those states, and then eventually, once it's covered out the whole state space, it's going to have an optimal policy. Does that make sense? You don't need to. You don't need to because of this exploration bias that you bake into the algorithm. And that's one of the advantages of model-based methods is that they can do this kind of long-term planning to do exploration, right? They're not susceptible to like just hoping, waiting for the winds of chance to take you throughout the state space. They're more complicated, and you'll see that in the code. Like it's quite a bit of code to code these things up and get them working, because you have to not only have a model that you're doing your updates on, you also have to get VI to work, value iteration to work, or whatever your planning algorithm is has to work as well. But in exchange for that extra computation, you get a very systematic policy that goes out and explores the entire state space in a really nice way. You had a question? No? OK. All right. All right. So like basically, the idea is you're going to estimate the MDP parameters, which are the reward function and the transition function. You're going to apt optimally at every time using your best estimate. And the way that you get exploration in this approach, because if you never go to those unexplored states, then it'll just like, as soon as it finds any kind of cookie, it'll be like if you set the reward to be negative infinity, as soon as it did something, it would be like, that's better than nothing, and just kind of do a circle, get stuck in a local minimum. So you have to set the reward to be high. What if you set the reward to be like in the middle somewhere? What would it do? So like, what if I know, I don't know where, but somewhere there's a reward of 1,000. But most places, there's only a reward of 1. And then my penalty for being alive is -1. So what if I set my, maybe I'll say my reward for being alive is like 20. No. I'll write this down. That'll be better. So somewhere, there's 1,000. Most places, it's 50. And my penalty for being alive is -1. OK? So what if I set my Rmax to be 100 when I do this initialization? What's it going to do?
Probably keep exploiting the suboptimal.
Yeah, so, well, right. So like, if it's 100, it's kind of better than 50. So it'll keep trying to explore. But as soon as it gets to 1,000, what's it going to do?
Yeah, so it won't go to the
Yeah, so once it finds that 1,000, it's going to stop exploring. It's just going to go get 1,000 reward over and over and over and over. Is that good or bad? What? Yeah, maybe it's good. Yeah, it depends what you want. Somebody else said bad. Why might it be good?
If 1,000 was money, then you
Yeah.
get lots more money by staying at 1,000.
Yeah, so your cumulative return would be higher. Why did somebody say it was bad? Yeah.
I don't know.
I heard somebody say no, it wasn't good.
But
Yeah.
like you don't know the value, then you need 40, and then you never get 1,000.
Right, but let's say you find 1,000. Right, so Rmax, if it's 100, it's going to drive you to explore. But once you find a path to get 1,000, you're not going to explore anymore.
But if it was 40,
Yeah.
50 when you get stuck. Because you'd be like, oh, that's great.
Yes, you're right. But so I was saying our Rmax is 100. I know I said different numbers. Yeah. Does that make sense?
Yeah, but I was saying like if you have to pick that,
You have to pick that. Yeah, you picked that.
If you, at the beginning, yeah.
Yeah.
Incorrectly.
So if you picked it to be 40, this is incorrect, right? Because it's supposed to be a bound. It's supposed to be the highest possible reward. So we could think about 40 too. The same thing will happen, but it'll happen here instead of here, right? So if it's 100, and I find that 1,000, what's bad? What's gonna happen that's bad? It's the same thing that would happen if I picked 40 and instead of 50.
God, but you said you're going to go.
There could be a 10,000 out there. That's
Well,
better than one.
but I'm telling you, there's not. Like the best is 1,000. So it's not that. It's not quite that. Yeah.
If you pick 100, there could be anything between 100 and 1,000 that if you land on it, you'll stop searching for the 1,000.
Yeah. So there might be something in between, that, and it might not be as good. So I might not find. So even though once I find that first 1,000, I'll start exploiting it right away. I'm not going to finish my exploration, right? And there might be something better in between there that I won't go and grab. Lee? Yeah, that's exactly right. So I might not find the optimal policy. Sometimes that's okay, right? Depends. Again, depends what I want to do. Depends how my domain is structured. Depends what I most care about in solving this problem. Sometimes you just want a return. You don't really care if you found the optimal return. As long as somebody gave me $1,000, I'd be pretty happy, and I wouldn't be questioning like whether I could have, made $1,002 as long as I got my $1,000, right? In other domains, you care. Like it really depends on the problem and what's important to you. Okay. But for the project and stuff, for lots of problems, you're defining the reward function based on what you want the agent to do. So you can actually, it's not that hard to come up with a max reward because you decide, I'm going to give my robot a cookie if it hands me the eraser or something, and then you decide how big the cookie you want, and then it sort of all comes out of that. So it's not generally too hard to pick the value for Rmax. So here's the pseudocode for the algorithm, and I recommend you read you read it. Maybe we'll go through it right now, but the source code, this is from that same paper that we linked to on the website, and the source code, the code in the project follows the pseudocode very closely. So there should be a good match between the document and the algorithm that's given the pseudocode and what you're expected to implement. And it's, as you can see, just like if you just stare at it without really reading it, like it's kind of a lot that's going on in this algorithm. But there's kind of two main steps. So the first step is up here where it's doing update model. Okay, so that's where we're basically estimating our distribution. We're counting stuff up and estimating our distribution for the transition function and for the reward function. And then the second part is down here, where we call VI on our learned model. And the Rmax stuff is happening right in here. So like when it reaches an unknown state that it hasn't observed before, it sets the initial reward function value to Rmax. So if we kind of walk through it, you can see at the beginning it picks an action from the policy. What's that policy going to be at the beginning before we run any updates? What's that? Yeah, random. I mean, it sort of depends how I code it up, but like because my VI might decide, it just depends what order I iterated through my states in my VI implementation, but essentially random. It's going to pick a random action. It's going to observe R and S prime. And then here's these counts, right? So C of S, A, and S prime, just like we did in the maximum likelihood estimate. It's how many times I saw S, I took A, and I ended up in S prime. And increment C of S and A, right? So that's so I can do my normalization. And then our sum of S and A is how much reward I have observed when I was in S, I took A. So these are just the things the bookkeeping you got to do to make those maximum likelihood estimates with the tabular representation, right? So I'm still going to have a big matrix that's indexed by all my states and all my actions. And then there's some threshold that says if I've been there enough time, I'm going to decide I know what that state is. So I'm actually going to compute my maximum likelihood estimate for the reward. So here, R of S of A equals R sum of S of A divided by the number of times. So that's the average value I got of being in S and taking action A. And then my count, so for my transition dynamics, I'm just going to do that same thing. C of S, A, S prime divided by C of S and A. So that's just what we wrote down before on the board for doing that update. If we haven't been there before, then we set it to some initial parameters. So this is because you could initialize those matrices at the beginning. Like you could basically make a big array of all the states and all the actions. But the reason to do it in this style is it kind of lets you see states that you haven't been in before. So in real RL, like you don't actually even know all your states. Like you see them as you encounter them. So this is doing this kind of incremental update. Then once you've done all that bookkeeping, then you call VI. So then that's a whole other block of code that I'm not going to put up today, but like you saw it last time. And you have to implement it for your project. So you call VI to come up with a policy, and then choose an action according to that policy based on your update. Does that make sense? Questions? Cool. All right. So what I thought would be good is to see this in the Thompson sampling setup from before. So basically, here's some Python code that does it. This is simpler than what you're doing for your project, because this is for bandits. So the way that we don't actually have to solve VI. We don't have to have a full implementation of VI. And we could do it, like right? It's an MDP, but we can kind of shortcut that whole thing, and just do an kind of an Rmax. So I have this method up here called Rmax policy. We'll look at it. It's basically using the model to compute the maximum expected rewards, and then picking that action. So that part kind of feels like Q-learning, right? Yeah. But in Thompson sampling, it's kind of all like it's such a flat problem. There's not much difference between the reward function and the value function because like there's not that much future. But in a problem where there was future, you'd actually have to do VI in that step to actually go back to a policy. Yeah.
So actually, I have a related question. So
Yeah.
what's the difference from Rmax with thermal difference learning?
Temporal difference learning?
The thing we learned before.
Q-learning?
Yeah.
Yeah. So let me show. So the thing we did before Q-learning, is that what you're talking about?
Yeah.
Yeah, they're kind of related, right? Because in that version, we were also learning the transition dynamics, right? What's the difference between learning? So in temporal difference learning, we were learning the transition dynamics and we were learning the value function. In Rmax, we're learning the transition dynamics and the reward function. Okay. And the different, I mean, the different, like how this plays out. Well, actually, I'll show you in the next slide the difference between Rmax and Q. Actually, I'll ask you to think about it before I show you the slide. So let me go through the code, and then maybe you can start thinking about now the difference between Rmax and Q-learning. What is the difference in behavior you're going to see between those two approaches as it's learning? So here, so like basically, here's how you can sort of do Rmax. I did it with default dicts because then you don't have to have a big matrix in advance, and it sets the initializations, right? And this is basically following up the pseudocode. So it picks the action, samples a reward, does its updates, and then decides whether to, once it's seen that state enough times, it decides whether to use it in the model versus not. And for things it hasn't used, it assumes that it's going to take you to this mythical state of happiness where you get lots of reward. So that encourages it to explore. And when we run it, I was running it. So I'm doing it with Thompson sampling. You can kind of see it already up there. I'm doing it with Thompson sampling, a random agent, and policy search, which we'll talk about next. And you can see it doesn't do as well as Thompson sampling, but we're beating our random agent, and we're kind of learning our model as we go. And again, the Thompson sampling is nice when you can really understand the domain. It's kind of an upper bound on how well you can do. It's actually provably optimal for for maximizing your return, minimizing your regret. So that's giving you a sense of what that looks like. Okay, so now the question was sort of what's the difference between Rmax and TD learning, Rmax and Q learning. So let's imagine that we're running Rmax and Q learning on an RL problem. What do you think the difference is going to be? What's the performance curve going to look like for one versus the other? Let's say Q learning with epsilon greedy. So first of all, what do all these curves look like? They all kind of look the same if your algorithm is doing anything at all. So there's a graph usually. And there's usually an x-axis and a y-axis, right? So what might be interesting to report about the performance of one of these algorithms on the y-axis? What might we want to measure? That's loud. What are we trying to do as we learn? We're in AI Vegas. What do you want to have happen? Yeah, you want reward. How much reward am I getting? So you said average reward. That's so how would you define that?
So I sum all the rewards I got.
Mm-hmm. Yeah. So every time I do something in the world, I get it and end up with a certain amount of reward, and I sum that out and see what I got. Good. You can also so that's good. You can also maximize your overall reward, like your discounted reward, because over time. But average reward, I think, is what the figure I'm going to show next actually shows. And what is going to be on the x-axis? What's going to be here? Yeah, how many times I've been alive? Number of actions. How much experience do I have in the world? And what is the curve for any one of these algorithms going to look like? What's going to be like at the beginning? I haven't seen anything in the world and I'm trying to wander around. Is it going to be high or low? What's that? Zero. Yeah. Well, maybe not zero. You don't know, but it depends. Because some domains are really dangerous and they give you lots of penalty. But anyway, let's just say it's going to be relatively low on a 0 to 100 reward scale. And what's it going to be after I've learned? What do we hope it's going to be? Higher. Yeah, it's going to be higher. Something like this. And somehow there's going to be some line that connects them. And typically what it looks like is one of these guys. There's some kind of learning that happens fast, and after a while I'm kind of asymptoting out. And there might be some known optimal policy up here that I'm approaching. If I act in the way that's known to be optimal. So almost all of these curves are some version of this. Sometimes it's cost, and then it's like this, but you have to. And it gets really confusing when you read papers and they switch back and forth in the same paper between reward and cost. It drives me crazy. So it always kind of looks like that. Okay, so Rmax and Q learning are going to kind of look like that. What would a random thing do? What would it look like for a random agent? What would this look like? What do I draw here? And just sample uniformly for my actions. Well, this is going to be average reward. And I'm not changing my policy. My random agent is not going to change my policy over time. So is it going to be curve? Is it going to change with the number of actions or not? Is it going to be constant? Yeah, so what's that going to look like on a graph? A line. It's going to be a horizontal line. And where it is, you don't know, because it depends on what the domain looks like with that random policy, but probably going to be lower than my Q learning guy. So now let's imagine the other extreme. Let's imagine that somebody out there knows the domain. They've explored the entire thing. They've done all their learning. They've coded up the optimal policy, and they handed it to me. Let me stick my laptop. They've handed it to me. So what's that going to look like? And I start running it at time t equals 0. So first of all, is that going to change over time as I learn actions, as I see more experience in the world? No. So it's also going to be a line, right? And probably like it's this line up here, right? Like this is the optimal policy that I got. And then my learning agent is like starting out down here somewhere and going up here, maybe above random, maybe below, depending on how the domain is structured. Does that kind of all make sense? So now tell me about Q-learning and Rmax. So let's think about at the beginning, Q-learning versus Rmax. You know, the first few times it's running around in the world, what do you think is going to tend to get higher reward? None of this is like absolute. This is kind of like depend on the domain, but like typical domain. You know, there's some reward out there. It's not everywhere. There's some good stuff. There's some not so good stuff. Yeah. Yeah. Why? Yeah. Why do you think that? Yeah. Yeah. So like, what's Rmax going to do with the Rmax thing? What's that going to make it do? Explore, right? So at the beginning, is it going to get as much reward as Q-learning, which is going to like as soon as it sees something good, epsilon at 1 minus epsilon percent of the time is going to exploit. So we kind of think Q-learning is going to be kind of up here somewhere at the beginning, and Rmax is going to be kind of down here somewhere. I'll erase this one because this was our model one. I should have different colored chalk. All right. Rmax Q-learning. Right? We think Q-learning is going to be better at the beginning. After a few experiences, at the very beginning, they don't know anything, right? But once the Q-learning finds something, it's going to try to go there a bunch of times. Whereas Rmax is going to be like, explore the whole place as fast as I can, because everywhere that I haven't seen is better than anywhere that I have seen if my Rmax is set to the max. OK, so now let's think about at the end. So I've run around in the domain for a really long time, and I've learned everything that I can learn. Where do you think Rmax is going to be? Where do you think Q-learning is going to be?
Rmax is going to be higher.
Yeah.
Qmax because it's found potentially more optimal solutions.
Yeah, Rmax has like gone through, explored the whole thing. It stopped doing its exploration bias thing. So probably it's going to be like up here. I'll erase this one. Can you guys see that? No. OK. I'll compress it. Can you see that? So OK. I'll move my screen. OK. So Rmax is probably going to be up here, and Q-learning is probably going to be down here. X, right? So if I kind of draw, I've drawn them as straight lines, but they're probably sigmoidy, curvy lines like that. So there's going to be a range where Q-learning does better, but after a while, Rmax is going to finish its exploration and start doing exploitation, and that's probably going to be better than Q-learning. Even if I do some tricks with Q-learning epsilon greedy. So like I could decide, well, maybe I'm not going to do so much epsilon greedy. After a while, maybe I'll just switch and stop. I'll just start exploiting all the way. So then Q-learning will get to the optimal policy. That's known to happen. Like it might do like a step function and jump up to the optimal policy. But Rmax is still going to get there faster because it's doing the systematic exploration as it goes. So every time it sees a new state, it's going to take special efforts to get over there and understand how that part of the world works and try to figure that stuff out. So I'll show you an example of this from that same paper. This one. So this is sort of showing that same pattern. So here's the episode number. They show average reward, just like you said. And at the beginning, so the Q-learning is the blue line, and Rmax is the dashed line. And at the beginning, Q-learning is doing better, but then after a while, Rmax passes it. So Rmax is doing terrible, right, at the beginning, because it's just like ignoring everything that it's learned and like being like, I just got to understand this whole space as fast as I can. But after a while, it starts to do exploitation. It starts to explore more. It starts to switch into exploit mode, and then asymptotes out higher. But you see that Q-learning, as it goes, is coming closer and closer and closer to Rmax. It's catching up in the limit. Does that kind of make sense when you might want to use one versus the other. Cool. Put this back down. All right. So the advantage of these model-based methods is that it really lets you be explicit about what you know about the world. So I can control my exploration in a very nice way because I can sort of reason explicitly about what parts I've seen and what parts I haven't seen, and also how to get through the world to the parts that I've seen and to the parts that I haven't seen. And there's there's like sort of one paper after Rmax is something called quick learning, which Michael Littman did here. He didn't do it while he was here at Brown, but he did it when he was somewhere else. I don't know if it was at Rutgers or Duke or what, but and quick stands for knows what it knows. So that's where the agent is explicitly tracking with bounds how much it knows the transition function and how much it knows about the reward function. And then when you ask the model, it's either going to tell you the answer, and the answer is going to be right with very high probability, or it's going to tell you I don't know the answer, and then you can decide to explore. So that's in contrast to having this threshold here, where we count up if C S of A is greater than or equal to M, then at some point we're just going to flip a switch and start to use our learned knowledge. So the quick learning stuff will look at the variance of what you're seeing and try to put a bound on it, rather than just having a threshold that you got to tune. Okay, so that's Rmax. Any questions about that before we switch to a different approach? Yeah.
I don't understand why we're learning stuff from the middle of the everything.
Why it starts?
Starts at the middle of the everything.
Instead of all the way down at the bottom? Yeah. I suspect it's because it finds something fast. Like, so it looked like it's showing 0 trials. It probably has to, I don't actually know. I suspect it has to do with the structure of the domain. And so this is the taxi domain, so you're supposed to be like driving around and picking up passengers at like red and taking them over to green or something like that. And I suspect that the way that Q-learning, like it maybe finds something good fast. Like I would guess that the random policy is around where Q-learning starts. And then it finds something good and starts doing better. Whereas Rmax is like going off and like deliberately not picking up passengers and stuff because it's going to explore the whole thing and then come back and start to pick up passengers and go from there. But I don't know. I actually didn't. This is from the paper. I didn't code it up. I think you had your hand up first. Yeah.
So probably I think so. For the very first step,
yeah.
they should get the same rewards. So probably the very first point is the same, but
yeah.
just the 1 point. So
yeah.
of course not counted.
Yeah, they might also.
Like there
yeah.
is a very steep one.
Yeah. Yeah, I'm not sure. I mean, it might be that they're not plotting that very first one, and they are the same, and they only plot in the second one. It might be that they plotted after the first episode, and it's learning during the episode, so like it might be changing inside. These are good questions, though. Like when you're really trying to understand what the paper is telling you, it's important to get all these details. So we had, one of my students was implementing an RL algorithm over the summer called POMCP, and these questions that you're asking were very important to try to, because we were trying to reproduce the same curves that they got when we implemented our, because we implemented POMC. He had a C implementation and we had a Java implementation of Burlap, which James was going to talk to you about yesterday. And we were like tearing apart the paper, trying to figure out like why we were actually getting better performance than he got on the same problem. In our Java version, we were tearing apart the paper, trying to figure out like what we were doing that was different from what he was doing. And it was a lot of stuff like you're talking about, like did we start at the same time, and was our state space defined in exactly the same way, and how do we handle the case where it doesn't find a good answer, and what kind of knowledge do we give to the algorithm? So that's a good way to be thinking about this stuff. You had your hand up? Yeah.
Is it fair to say that in practical scenarios you learn as a shorter training period?
I don't really feel like there's consensus about like in the way that there is for like machine learning, like with with logistic regression and SVMs and naive Bayes. Like there's lots of algorithms out there, but everybody will be pretty much like, yeah, you should start out with SVMs or logistic regression. Like that's, the right thing to do most of the time. And it's okay to use naive Bayes because it's easy to understand, especially if you want to like marginalize out your features. But with RL, I think it's just less well understood. We can run these experiments for specific domains, but the structures of the domains are so different that it's harder to make these general claims. And there's a bunch of work in theoretical RL, which I don't understand, where they try to prove things for any domain, any kind of problem. But I don't feel like there's a lot of questions that are very natural, where the answer is we don't know the answer. Like there's no known answer in the literature for which one is better for a lot of these algorithms. Like which one is going to converge faster, which one's going to give you better reward overall. A lot of it is sort of getting an intuitive, like right now a lot of it's more of an art than a science. Like it's getting an intuitive feel for these algorithms or for what you want out of your algorithm. So like in our work on Minecraft, I just saw yesterday, like one of my students made a Minecraft Forge mod. You were telling us to use Forge, so that you can run burlap, which James is going to tell you about next class, inside of Minecraft to control a Minecraft agent. And have your guy run around and do stuff. And one of the first things I want to try with this is Rmax. And the reason I want to do that is because I think it would be really cool to have that model explicitly. Like knowing the transition dynamics and the reward function for Minecraft learned by playing in the real Minecraft domain. I don't think it's going to work because I think Minecraft is way too big. But I kind of want to try it and see the ways that it fails and then use that as a jumping off point for future research in this area. And you might make other decisions for different reasons, depending on the details of your domain. OK, so we talked about Rmax, which is kind of, maybe I'll go back to this slide here. Oh, that's the beginning, end. This slide here, so we talked about Q-learning and Rmax. Now we're going to go down or up, I don't know which frame of reference you're going to use, and we're going to switch to talking about policy-based methods. Okay, so again, this is sort of changing what we're going to estimate about our model. You could think of this related to the machine learning things we were thinking about. We could do that underlying distribution like we were doing with naive Bayes, like a generative model. We could have a discriminative model, or we could just somehow try to predict the right answer directly without thinking about probabilities at all. And these policy-based ways are analogously, and the one we're going to talk about is still going to use probabilities. But we're not going to try to think about our value function. We're not going to try to think about our transition function or reward function. We're just going to try to estimate a policy. Okay, so we're going to somehow parameterize our policy and then twiggle its model parameters to try to figure out what are good actions to take directly. Okay, there's going to be none of this value function business and then maximizing over the value function. There's going to be none of this VI business. I'm just going to have my algorithm tell me the action. It's going to learn the action to take. What do you think of that? On the face of it, like what do you think the trade-offs are related between, let's say, model-based and policy-based? What are you losing when you do that, if you do policy-based? What don't you have?
So I cannot apply the domain knowledge of the problem.
So it's actually a little different. It's a different type of domain knowledge that you can apply. So I can't apply my knowledge about the transition function, at least in a direct way, right? Because I'm not estimating it at all. I can't apply my knowledge about the reward function. So that's a disadvantage. What's something you could apply though? If I'm directly picking which actions to take, what knowledge could I have that might be useful? I'm just going to pick some actions. So like a sort of uniform prior would be like I'm going to randomly pick actions at the beginning and then try to figure out which ones get more reward and then do those later. But if I wanted to apply my knowledge to the domain, what knowledge could I add to make that go faster? What could that look like? This is used a lot in robots. So like, you can imagine like a car. Some of this work was done like teaching a robot to steer a car wheel. Go this way, go that way. Maybe I phrased the question. It's not a trick question. It's just so like, right, I'm going to try to pick the actions I'm going to take. The knowledge that I could apply is knowledge about what are good actions, right? So maybe it's almost too recursive, right? But like, if I know something about what tend to be good actions in the domain, in particular situations, if I've got a good prior on actions, or I've got a good space of actions in the first place, like I can define the space of actions I'm considering when I define my domain, then that can help my guy do better. And so that, and it turns out in robotics, often that's the case. So like, I know how to drive a car. It's not too hard to get a human to do that. You can actually collect direct observations of what a person is doing as they're driving a car in different situations. And you can use that to try to induce a distribution on what are good actions to take in different situations, as opposed to just having your agent wander around randomly and act in the domain. This is used a lot in robotics because in robotics, lots of actions are really terrible. Like, there's a lot of things you can do that just cause your robot to go off a cliff. And it's really sad. And we don't want our robots to do that. We don't want our robot helicopter to go crash into a wall. And so we don't generally, like this. So what would Rmax do if I put it on a robot helicopter? Yeah, right, you're laughing, right? Why are you laughing? Why is that funny? What would happen? It would go crash into every single wall, right? Well, there might be a reward if I do that. It doesn't know. So in some situations, you don't want it to like go off and like crash into every single wall. That would be really depressing, and you'd have to go through a lot of robots, and it would be really not fun. So instead, what you want to do is really constrain the space that it's in and say, well, look, don't crash into walls. If you're too close to a wall, just don't do it. Constrain the space of possible actions to ones that look good, and then optimize within that space. And these are policy-based methods. People use policy gradient a lot to do this. And actually what I wanted to do, I'm going to zip forward now, policy search. This is relating back, if you guys remember from the beginning of the semester, right at the beginning when we were doing search, we read that paper from Branovan. Yes? Some of you remember? About Microsoft tech support articles. And what I thought would be fun to do now that we've kind of covered all this stuff is to go back to that paper and cover it again, because that paper was also using policy-based methods. And it kind of fits into this framework. So this idea that we've got some policy of S and A that's parameterized with some parameter vector theta, and you could do this in many, many different ways. You know, pick your favorite machine learning algorithm, and that'll be your model parameters. And maybe in this world, it's P of A given S and theta, but just like you can go back to machine learning, you could have decision trees or something else in here as well, instead of a probability distribution. So in this sort of bit of math, it's using an exponential logistic regression kind of model, right? So my theta, I'm going to have some features of my states and of my actions. I'm going to go normalize it out, and that normalizer makes it be between 0 and 1 and sum to 1. And the thing that I'm going to try to update as I act in the world is my parameter vector theta. Hit the chair. So you initialize your thetas to 0. That's going to give you a uniform distribution at the beginning. And then for each iteration, sample an action history from the policy. So do something. And then execute it. And then see how much reward you got. Right? So was it good or was it bad? And then update your thetas in proportion to your rewards. This is stochastic gradient descent. This is a kind of simulated annealing style of algorithm, or a particle filtering style where you're kind of jumping around in this space. And you're updating the thetas in proportion to the reward times the gradient. And this has this nice, pretty form for the gradient. Let me put this down. It's already out of it down. Well, it's not quite cut off, so you can survive. So if you take the derivative of this guy, what you get is the feature value minus the sum. So what is this sum? It's the sum over all the actions, right? What does that correspond to? There's a probability in there. Yeah, it's an expected value. Yeah? So what's the expected value of?
What you get based on that policy?
Yeah, it's the expected value of the feature according to the policy, right? Because this is the distribution that I've got right now with this value of theta, right? So I'm summing over all of the different feature values of the state and all the different actions I could take, and I'm weighting that sum according to my policy. What am I subtracting that from? It's like an error term, right? Like, so what's that other term that I'm subtracting it from? Yeah. Yeah, it's phi of S and A. It's the feature value. So I'm taking the difference between the observed feature value that I got and the expected feature value. That gives me kind of an error term. And then I'm updating my gradient in proportion. That's sort of where the gradient comes from. And then I'm moving my thetas in the direction of that error term, multiplied by the reward. Then this comes out, if I actually take the derivative of that, I do lots and lots of algebra. I've done it. It's not all that fun. You have to use the chain rule and stuff. And it all cancels out, and you get this. It takes a little bit of manipulation to get it into a form, because when you take the derivative, you get like exponentiating things. You have to like manipulate it to get to something where you can replace it with this recursive form. But I wanted you guys to know that was possible and get to you the intuition behind that nice recursive form. Okay, so like this is sort of the slides from before, but like I said, I thought it would be fun to go through it again. So like the idea was that there's these instructions in Microsoft tech support articles, and you click Start, point to Search, and then click for files or folders, and somehow that translates into actions in Windows, like in Microsoft Windows. And what he was doing, we had this problem formulation. When we did this the first time, like you guys were doing the problem formulation, but we already did that, so I cut some of that stuff. So like there's the states, which is like the state of Microsoft Windows, the actions of all the mouse clicks that you could do, the goal test, and the path cost. So how much did it cost to get from the start to the goal? And so you had this kind of, remember this funky state space where you could cross out the words that you were going to process, and that would translate into an action. And then afterwards, you had this revised state. So after that, you said there's some more words that you have to cross out. Same deal. So then you click select run. Now we're going to left click on run. We're going to cross out select run, and then have this updated revised state there. So it does that, and then this big distribution of possible states in action. So what would Rmax do in this world? Where there's this huge state space explosion. Yeah, it would explore like all of Windows. Yeah, it would run around in all of Windows before it tried to get any kind of exploitation happening. And that would take a long time. Okay, at the end, it would know all of Windows. So that would be pretty cool. But it would take it a long time to get to that point. So that's why I think Rmax in Minecraft isn't going to work so well, because it's going to try to explore all of Minecraft. But I just really like the idea of having a model for the other stuff that we're doing in Minecraft. That's why we're starting out with it in that way. But the reason he went with policy-based methods is to try to avoid that, to prevent that from happening, because it can kind of try to this is the same function stuff. So we can kind of learn this policy function and not feel this need, this obsession with like trying to figure out where all of Windows, what's going on in like all of Windows and the whole entire thing. And it's doing the same kind of update that we just talked about with this theta prime equals theta plus d theta, where d theta was that equation I put before with the expected feature value minus the real feature value minus the expected feature value. And theta is just a weight vector that's associated with each one of these features. And then you get the reward earned in the train set that tells you which directions to move your theta. So if you did something good, then you'll move in a good direction. You'll move your feature weights higher. You'll try to do that more frequently. If you did something bad, it'll move them lower. Try to do it less frequently. So that's going to try to, it's going to be subjective. So it's going to be susceptible to local minima. There's no guarantee that this is going to converge to the optimal place. But what it is going to do is wherever you are, it's going to try to get locally better. And it's not going to feel like it has to explore the whole space in order to do that. Does that kind of make sense? So the local minima idea is like where Rmax is like, Rmax doesn't want there to be any local minima. It's going to find you the globally best policy. But in a world that's so huge as Windows, where's this picture? In this picture here, this picture, in the world that's huge as Windows, finding the global maximum is, even though you'd love to do it if you could, it'd take too long. And so you settle for a local algorithm. And it goes much faster, but like it enables you to learn useful things without having to find the globally best answer, globally best spot. All right. We saw this, the learning algorithm. So that's the feature update with their stuff. And then remember their features were like whether the object was visible or invisible and crossed with the features of all the different words that they could take. So they had 4,000 some odd features. And that's pretty common when you're doing just like in your naive Bayes stuff, right? So like the same idea where you had features for whether you saw this word. In this case, it's features for seeing the word crossed with all of these other features of the low-level state space. So that's how they combined the word level features with the Windows features. They just took the Cartesian product, and they got like 4,000 something features. This feels really weird the first few times you do it, because you're like, how can you possibly have that many features? But what it does is lets the algorithm, like you're just being agnostic to what the algorithm's going to learn. You're just giving it a big old feature vector and letting it try to put all the pieces together into the learning. That's the same equation from before. And then this is the results that they got. So they didn't show. I think in the paper they have the curves over time, like we were drawing over there for Q learning. But they also have random action. So this is what happens if you click randomly in Windows. You get to the right place 13% of the time. The majority action. So that was when you. What do you think majority action is? From the name. It's another baseline. It's a pretty common one. It does just a little bit of learning, but not very much. Yeah.
All actions.
Yeah. Yeah. So I picked the action that's most often the right action by counting up.
Always the same.
Yeah, always the same action. Yeah. So like click the start menu. It's something like that. And that does a little bit better than random because, it's probably not click the start menu. It's probably somewhat parameterized based on the state. So once you click the start menu, you can't click the start menu again. It's probably like click a button with the mouse. Or not typing text, because I bet you do that lots of the time. And then environment reward is using this reward function defined by the environment. So what they were doing was looking at the overlap in the text report article and words on the screen. That was their environment reward. And then they also had supervised versions of this problem. So they did something like you did in the machine learning section with annotated data in order to predict the right answer. So what do you think supervised would look like? What would the training data look like for supervised? For full supervision? Let's say we're going to learn this action distribution. I think I have it. This guy. P of A given S in data. What would supervision look like? I'm going to do, this is logistic regression, right? I'm going to do logistic regression. So I'm going to train my model. What am I going to train it on? What data do I need to train my model? need examples of something, right? Like, what are my examples going to be? If I want to learn P of A given S. So like think back to like naive Bayes or something. I'm doing spam filtering. I want to predict spam or not spam given my email. What did I need to train that model? What's that? Say it louder. Sorry. I can't hear you. I need sample emails of both classes, right? I need some emails that are spam and some emails that are not spam. So by analogy, what do I need for this? The probability of A, the probability of the action given the state. What do I need? And I want to know, I want to pick the right action. Yeah. Yeah, somebody following, I need to know, to do supervised learning, I need to know the right action for all those different states. And the way that I could get that is by having somebody follow the directions and see what actions they were taking. Now that alone isn't quite enough, right? So for this model, if I'm going to learn P of A given S, and I've got a whole history. So let's say I have somebody sit down and they go click, 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 click. What does that correspond to in terms of what I've observed here? Each one of those clicks is what? It's an action, yeah. So that's like a whole bunch of actions and a whole bunch of states. To do supervised learning, I have to do one step more, right? What do I have to do to that history? Yeah, label it. Label it with what? I'm going to assume it's good because the person did it by following the directions. But what I don't have is this alignment with the text. Right? So like I don't know, there's this whole paragraph that they were following of instructions. And I know somewhere, somehow, like remember the state space, this funny thing where they were like crossing out a bit of text? I don't know that. In order to compute this in a supervised way, I've got to actually annotate all that stuff. And that's, he didn't quite do that. He played a trick to not have to annotate. He annotated what you said, I think, in the paper. But he had to play a trick to do that in order to infer that alignment between the words and in the command and the individual text. But then he's showing that like in the environment where without doing that annotation at all, he gets 65%. If he does a little bit of that annotation, not all of it, he approaches the performance of the fully annotated version. So I really like this paper because it kind of puts everything together that we've covered in the course. It's a really great example, I think, of applied AI, where they do a little bit of search, they do a little bit of machine learning, they do a little bit of RL, and the overall thing is something really cool because it's actually reading these instructions and following stuff in Microsoft text support articles. So it might be fun if we're not requiring you to do this, but like it might be fun to go back and look at it again and see what it makes you think about and how it puts these pieces together. This is the kind of thing I hope you guys do in your careers after you go out after taking this course. Like you're able to. No, doing any one of these things it's a lot of work and there's more expertise maybe that you need. But I hope you have the tools to go out and acquire this kind of knowledge and figure out which parts you need in order to put these pieces together in order to do cool stuff. All right, thank you. Hey.
What is Thompson research?
This was yesterday. Yesterday.